Hello again, this is Michael Sulak with a look into section 9.2, which is about estimating the mean of a population. In section 9.1, we looked into confidence intervals for the population proportion. We took the point estimate for our population proportion and we added and subtracted the number that we called the margin of error. And so the point estimate for the population parameter, in this case a proportion, is always just the corresponding type of number from the sample. So we're trying to estimate a proportion for these guys. Put p hat in the middle, and then we added and subtracted the margin of error, which was two numbers. The first one, which is a percentile, and we called that thing z of alpha over 2. And the second one, it's wondering how variable is the sample proportion. I didn't talk about this in the last video, but if we wanted to find the standard deviation of the sample proportion, back in chapter 8, we talked about how that thing was this quantity. We could use that to find probabilities associated with the sample proportion. If you think about this thing, what does it use? It uses p, which is a parameter. So this thing is a parameter, and this thing is hard to know. So what did we do? We needed to estimate it. And what did we use? We used something that essentially has the exact same format, but instead of using p, we estimate this thing by sticking in p hat. And this is the quantity that appeared in our confidence interval for p. So it's not the standard deviation of p hat. What is it? It's a value called the standard error of p hat. It's a statistic. It's a number that we could find based on our data, and that's what appeared in this formula. So now we're going to be in section 9.2, which is going to be a confidence interval for the population mean, for mu. And it turns out that this formula that we used before is going to have the framework for making a confidence interval for mu, which is but the fish that we're trying to catch is a mean now instead of a proportion. What number are we going to estimate the population mean with? Well, why would we use anything else besides the sample mean with x bar? So our point estimate that we're going to stick right in the middle of this interval now is going to be our sample mean. And then we're going to add and subtract the margin of error. And the margin of error has the same two types of quantities. It has a percentile, and it has a number related to how variable our statistic is, the sample mean in this case. So let's deal with the number on the right here first. If we wanted the parameter that talks about the variability of x bar, we looked at that earlier, which is just the variability of individuals in our population divided by the square root of the size of our sample. This thing is a parameter, and why is that? Because this sigma of x here is the standard deviation of x, which you would need to measure every individual in the population to know. We want to estimate this quantity. And so all we need to do for that is to estimate the population standard deviation with what? The sample standard deviation. That is S sub x. And so we have this quantity that looks very similar to the standard deviation of x bar. And just like with our confidence interval for p, we call this not the standard deviation, but the standard error of x bar. So that quantity is what's going to go on the right here. So, okay, we've got the standard error of x bar, and now we need this percentile. This is the major difference between a confidence interval for the population mean and a confidence interval for the population proportion. Let's look at the differences currently between these two formulas we've got here. You might see a subscript x on this s. I know your calculator does that when you find it, or you might not. Either way, it's the sample standard deviation. So let's look at the formula for the confidence interval for a population proportion and ask ourselves, how many numbers in this formula actually depend on the data, which is another way of asking how many statistics are used here, which is another way of asking how many parameters do we have to estimate for this formula. What quantities do we have? We have this z of alpha over 2. Does that depend on the data? No, that just depends on the level of confidence. And we've talked about how the more confident we want to be, the larger this number becomes. So that's not included. What about p hat? Certainly, there's one. P hat is estimating the population proportion. P hat estimates p. And then the sample size, does that depend on the data? Not really. When I say depend on the data, I mean depend on the actual values of the data themselves, and the sample size does not. So how many parameters are we estimating for this thing? How many statistics do we use? Just one. That's kind of a cool idea, is that this confidence interval only requires we use one statistic. We need the sample proportion to estimate the population proportion. And now let's ask these same questions about the confidence interval for the population mean. Okay, we've got X bar, that's a statistic. We've got the sample size, but we said that's not a statistic. We have this mysterious percentile value, but I'm going to tell you that just like the z of alpha over 2, this is not a statistic. But we do have the sample standard deviation. How many statistics are being used in this formula, this confidence interval for mu? There's actually 2. We have to estimate the population mean with the sample mean, and then we also have to estimate the population standard deviation with the sample standard deviation. That's kind of a big deal. There are twice as many statistics here, and what's easier to do, estimate one thing or estimate 2 things? There are more things that we don't know, more unknownness. I'm pretty sure this is not a word, but there's just more variability. This is a different type of situation. And so where did the z of alpha over 2 come from? That came from a standard normal distribution, and it turns out we are not going to use normal distributions for the percentile for our confidence interval for the population mean. We need a distribution with more variability than the standard normal distribution. This is an entirely new distribution, but I will tell you that it shares a lot of the same properties as the normal distribution. It's going to be a symmetric distribution. It's going to be bell-shaped. And the one we're going to use is always going to have its middle at 0. So what is this distribution? It was invented by somebody working for Guinness, who was a beer brewer, who just basically decided he needed an entirely new distribution. And what did this distribution end up being called? We refer to it as the T distribution now. When we are working with the population mean, the percentile we use is going to come from the T distribution. And so in this space here, instead of having a Z, we are going to have, you guessed it, a T. And we still get the same alpha over 2 because it's fundamentally the same sort of an idea as the Z of alpha over 2. It just needs to come from a different distribution. And so if you looked at this thing right on top of a normal distribution, it would sort of look more squished down. It has more weight on the outsides and less in the middle. First of all, we need to know which T distribution to use. There's a bunch of T distributions, just like there's a bunch of normal distributions. And just as a reminder, if we're choosing what normal distribution to use, every time you've used functions in your calculator using normal distributions, you had to give it 2 numbers. You had to give it the mean and the standard deviation. These 2 numbers determine a normal distribution. But a T distribution, the one that we use, is determined by a single number, which is not the mean and it's not the standard deviation. It has kind of a strange name. It's called the degrees of freedom. And so every T distribution has its own degrees of freedom. And which one are we going to use for this confidence interval? When we were doing confidence intervals for the population proportion, we always used the standard normal with a mean of 0 and a standard deviation of 1. But this time, the T distribution we're going to use is going to depend on our sample size. And how we do that is take the sample size and then get ready for it. You subtract 1. Holy moly. So great. We know which t-distribution to use. We just need our sample size and we're going to subtract 1. But now we also need to know how to find percentiles of a t-distribution. And with the normal distribution, if you remember, we had a function on our calculators called invnorm. If you have a TI-84 or something higher, you have an invt distribution, which in this invt, this inv still stands for inverse. And so the first number it needs, just like inverse norm, is going to be the area below. But instead of giving the mean and standard deviation, what do you think you're going to give? You guessed it, the degrees of freedom. The invt function only needs 2 numbers. And right now you might be thinking, my calculator is a TI-83 and I don't have this function. Well, you are in luck because you can program this function without too much difficulty into your calculator. And it's what I highly recommend. It's going to make your life easier. Ask me for instructions on how to do that, or look it up, Google invt TI-83. Having this function in your calculator is just going to make a world of difference. So that's just the main difference from a population proportion to estimating a population mean, is that the percentile we use comes from a t-distribution. But other than that, it still has the same format. It has the point estimate, plus or minus, all this stuff over here, which we call the margin of error. The margin of error is whatever you're adding and subtracting. Let's just do a problem from the book actually calculating a confidence interval for mu. So here's the problem I want to look at. It's from section 9.2, and I like these kinds of problems. These confidence intervals and hypothesis tests we'll do later because they're much more realistic. All we have here is a situation where we've collected some data, and I believe this is the author of the book, name dropping himself, Michael Sullivan, and he has some data. What's his data? It is the price of how much these flashcards cost. And what's his variable? It's the price of a 4 gigabyte flashcard. And he's got 10 data points here. So, okay, what are we supposed to do? Well, let's look at part A. It says determine a point estimate for the population mean price of the memory card. Well, that's a point estimate for mu. What is that? That's x bar. That's the sample mean. So I could either add up these 10 numbers and divide by 10, or I could put these in a list when I hit the stat button on my calculator, and then I go to edit. We've done this before, but it's been a little while. And I'm looking for 1 var stats, 1 variable statistics. It will find me the sample mean. That's the very first thing, 15.382. Even though this is dollars that don't have tenths of a penny, I'm going to leave it like that just because we're just going for accuracy right now. So done. Feeling good. Part C, which says 2 things. To construct and interpret what? A 95% confidence interval. And then it says to estimate the mean price of a 4 gigabyte flash memory card. It wants a 95% confidence interval for the population mean. We're certainly going to have to use this formula. So we need to find everything that's in that formula. Well, fortunately, I've already got x bar. That's going to be the middle. And what else do I need? I need the sample standard deviation, but 1 var stats gave that to me, which is a nice thing about using 1 var stats is I get the mean and the standard deviation all at the same time. And the sample standard deviation, which it calls SX, your book just calls S. And now we need this percentile. I know I'm going to have to use the inverse t function, and I need to find these 2 things. I need to find the area below, and I need to find the degrees of freedom. Because this is a 95% confidence interval, we're trying to find the value that basically makes a 95% sandwich, which means that there's going to be half of what's left, half of 5%, 2.5% below this number. So we've got the area below. And now we just need to know the degrees of freedom, which we said has this very complicated formula of the sample size minus 1. So what's our sample size? It's 10. So this is going to be from a t distribution with 9 degrees of freedom. So I'm going to use my inverse t function, which either came in my calculator or I programmed. And the area below as a decimal is going to be 0.025. And the degrees of freedom is going to be 9. And when I do this, I get negative 2.26. But like we mentioned before, we typically just use the positive quantity, 2.26. That is the fourth piece of this puzzle. Because I'm kind of a nerd and I like to be as precise as possible and I like to get things right, I just tend to take a second to write all the numbers down that I need. So I've got the sample mean, I've got the sample standard deviation, I've got my t-score. So ready to roll here. Let's get started on this interval. The nice thing about these intervals is they're a little easier to calculate because this quantity, the standard error of x bar, is just easier to find than the standard error of p hat because it only has 2 numbers. Just because I'm doing order of operations, like the adding and subtracting is going to be the last thing I do. So right now I'm just working on finding the margin of error, which first I need the standard error. So now I'm going to multiply these two quantities. And so now I'm ready to get the interval. I'm going to do x bar plus the margin of error, and that gives me the number on the right side of the interval. I always want to put the higher number on the right, and then I'm going to do x bar minus the margin of error to give me my lower value, 13.7071. And if it's bothering you that you're worth being that precise, you could round it. We're pretty sure that the average price of this thing is somewhere between $13.71 and $17.06. That's our net. So it does say interpret this as well, but I just want to get to part D because the only difference between C and D is our level of confidence. Now, instead of finding a 95%, we're going to find a 99%. What's that going to change? It's not going to change x bar. It's not going to change the sample standard deviation, S. It's not going to change the square root of n. It's going to change our percentile. So the only difference here is that we're not going to use 2.26 anymore. We need to find what? We've got the middle 99%, which means that there is half of 1% on either side, which is always weird to write, but it's 0.5%. So we want the 0.5th percentile now. So we just need to use inverse t. And so when we do this, we're expecting a bigger number than the 2.26 we used before because we're going to be more sure now. And actually it goes up quite a bit. It's going to be, if I use the positive value, it's 3.25 with a little bit of rounding. So what's going to happen to my margin of error? It's going to increase for sure. Not surprising, I'm using a bigger net. So what's my interval? $17.79 if I just go ahead and round it. And then on the low side is $12.97. So that is my 99% confidence interval for mu. So I still haven't interpreted anything because I just want to get to part E here, which says what happens to the interval as the level of confidence is increased? What happened? This thing is wider. It's a bigger net. So what happens to the interval as the level of confidence is increased? It gets wider. And then it says explain why this is a logical result. Because we are more sure that our interval will contain the population mean. So it just makes sense that as our level of confidence increases, our intervals become wider. We throw bigger nets. So now let's just pick one of these things to interpret. So let's interpret the 99% confidence interval. Why not? So like I said, we always start these with the idea that we are whatever level confident. We're 99% confident that the parameter, which in this case is what? It's the average price of memory cards. And this problem isn't that great because it doesn't really say where. This presumably means in the entire universe, but not everyone uses American dollars. This is probably in the United States, which would be a good for Michael Sullivan to have included in his problem, but he didn't. So we're not really going to mention where. We're just going to say that the parameter, the average price of 4 GB memory cards, is in our interval. So, and again, just sort of thinking about this is we don't have a date on any of this data as well. So if this was older information, then this might not actually be as accurate. But we're doing the best with what we have, and we are finding confidence intervals and interpreting them. And because we're dealing with a population mean, we have a percentile from a t distribution here. That's not a big deal. We just use our inverse t function, which either came with our calculator or we've programmed it in there. But other than that, it follows the same format as confidence intervals for proportions. We have our margin of error, and we add and subtract that to the point estimate to get the interval itself. So that's section 9.2. Just remember that on your final exam, you're going to have to figure out, are you making a confidence interval for the mean or a confidence interval for a proportion? Same thing on your project. If we saw a problem like this in the final exam, we just have to recognize, hey, what are we doing? We're trying to figure out the population mean. It even tells us, it has to tell us that. There's nothing in here about proportion or percentage or anything like that. This is dealing with mu. It's dealing with the population mean. So I hope this video helped you, and if you have any questions, please don't hesitate to ask me. And until next time, this is Michael Sulak signing off.